Good afternoon, ladies and gentlemen. I hope you had a pleasant break there. Some interesting discussion has taken place. So let's move swiftly on to our next session. We've talked a lot about the nuclear scene. Now we're going to move on to some aspects of the renewable scene. And to facilitate that discussion, we've got CRA's finest human factors team available today to entertain you this afternoon. So starting off, we'll have Adrian Wheatley, followed by Hannah Wright, and then we'll move on to another Hannah MacFarlane. Over to you. Thank you.
Cheers, Jazz. So yeah, this afternoon we're going to do something a little bit different for those people that don't really know human factors or haven't worked with human factors people before. My name's Adrian Wheatley. I've been doing human factors for about 20 years, mostly in the defence and defence nuclear industry with a little bit of rail. And to my right, I have Hannah MacFarlane and Hannah Wright. So, as Jess said, we're going to be talking about renewable energy, renewable power generation from a human factors perspective. It's more of a think piece, so we're not really presenting any research or a project that we've done, but it follows the brief. I like to think we hit the brief in terms of talking about target net zero, risk and safety challenges to support energy transition. So, very quickly for the uninitiated, human factors in a nutshell is about talking and taking a human-centric approach. So we think in terms of fitting the task to the human rather than the other way around. So what you can see on the screen are the commonly accepted HF domains in accordance with the UK defence standards. Obviously, other standards are available, but I quite like this in terms of just setting the scene for what the main HF domains are. And our focus is on the optimization of human performance shaping factors and minimizing the risk of error or failure. So by optimizing human performance, you'll also be optimizing productivity, efficiency, utilization, and safety. So on to renewables. Nuclear and fossil fuel energy production have their part to play in balancing grid supply. We anticipate nuclear energy is going to be around for a long time to come. We've heard a lot about nuclear energy this morning and this afternoon. But it's inevitable that more and more of our energy is going to come from renewable sources other than nuclear in the future, especially with the UK government pledging to achieve net zero greenhouse gases and emissions by 2050. And we've also had party political announcements this week about targets for 2035. So saying that it's inevitable is an understatement of the obvious because it is happening right now. In the UK today, over 40% of our total power generation is coming from renewables, non-nuclear, and it has done for a while now. We've already broken through and had record-breaking years in terms of obtaining more of our energy consistently from renewables than burning fossil fuels. And in good months, renewables have been the primary source of power generation, that being a mix of on and offshore wind, solar, hydro, bio, and waste. And in the last 10 years, renewable energy production has almost completely replaced coal burning production. Interestingly also, according to IRENA, which is the International Renewable Energy Agency, over 80% of new generating capacity is renewable. So while I'm quoting UK statistics, it's also important to highlight that the transition to renewable energy absolutely has to be considered on a larger scale because renewable energy creation is geographically sensitive. It shouldn't come as any surprise to hear that solar power generation's booming in sun-drenched areas like Australia and Africa, especially Morocco and the Sahara, and the UK, we all know, does well from wind power generation. Iceland are world leaders in hydro and geothermal power production. But other countries still remain heavily reliant on coal simply because it's cheap and they have an abundance of supply. So countries like India, China, and the USA, they still have quite a long way to go to reduce their reliance on coal and fossil fuel burning. But there are seeds of change. Countries like Germany, Portugal, Spain, Algeria, they're investing very heavily in renewable projects like this Saharan solar power generation project, with a planned network of power lines that will form a web of power distribution between continents. So while in some places we're seeing a trend towards decentralization and localization of power generation, especially in the UK, there are power generation and distribution projects that will operate on a continental scale. Now, nuclear power plants, traditional fossil fuel burning power stations and their feeder mines, they're great businesses for safety professionals for all the wrong reasons. They typically require people to operate in hostile environments or with hazardous materials and with complex machinery, or all three, which is a perfect storm for hazards and risks. So the continued development of nuclear power plants and the future waste management and decommissioning activities, that will keep risk management professionals busy for a long time to come. But what about renewables? Now, it's easy to understand that a significant incident at a power plant, a chemical or fossil fuel plant, has the potential to result in catastrophic consequences for human life and the environment on a scale that couldn't really be equaled by a wind or a solar power generation plant. Unfortunately, we only really need to look back at catastrophes like Chernobyl, Fukushima, Buncefield, Deepwater Horizon for our exemplars. It's pretty hard to imagine the catastrophic failure of a wind turbine causing a significant loss of life event or having such a huge environmental impact. But as clean as renewable power generation can be, it isn't entirely risk-free. Sorry, let me just... So let's take a look at hostile environments. This is where we have to build these renewable projects. Wind turbines are built in windy, isolated and exposed places. Solar power farms are in remote and hostile areas. Residential and industrial solar or PV panels are in hard to access places. And salt mining is in some of the most inhospitable areas of the world. This is a quote from a company that specializes in the repair of wind turbines. In this case, they were blogging about the repair of a fire damaged unit in the Ukraine. So I'll just read this. So as well as project delays and the global pandemic, Mother Nature threw everything at the team. Quite often the technicians had to deal with ever-changing weather, from severe snowstorms and black ice on every road to the extreme cold temperatures. A project of this nature has to be planned differently to working on any other wind turbine due to the exposure levels the team experience. There's no nacelle walls to shield the wind and no roof to protect from snow and rain. Freezing temperatures for the majority of January and February meant the conditions up top were also very tricky due to slippery metal surfaces, mixed with a covering of oils which had leaked from damaged oil hoses on the nacelle. Added to the usual expected winter conditions were the high winds, making available work windows few and far between, especially when man-riding basket use was involved. When we're talking about power generation, there's no getting away from high voltages. We've got stored power or energy, risk of fire from things like DC inverters and lubricants, an increase of batteries, increased usage, cocktail of complex chemistry, and in some applications we might even have superheated molten salts. the use of batteries is a particular challenge for the renewables sector. We heard a little bit about that this morning. In order to balance the system of renewable energy supply, we're going to need gigawatts of battery storage from a range of different battery types that introduce their own hazards. So large batteries are being used more and more as buffer storage to smooth out supply and demand. So we are having to open more mines and venture into new territories to extract the minerals required to produce them. Essential resources like lithium, nickel and cobalt are difficult to access, both geologically and politically, and there are some very real hazards associated with mineral extraction, production, storage, operation and maintenance. And the final piece of the jigsaw is hazardous machinery. So again, we've got big machines, complex systems with stored chemical energy and high voltages and high pressures. So as I've illustrated, as you've seen, renewable projects are operating on a massive scale in a combination of distributed microsites or using mega facilities. And to sum up, with renewables, we still have large-scale complex systems managing hazardous materials in hostile environments. And at the other end of the spectrum, we also have a large number of small-scale energy generation systems distributed over a large area. So whether that be a solar farm, a wind farm, battery storage units, or at the other extreme, domestic and local commercial installations mounted to millions of roofs across the country. So all of this has a number of implications for ergonomics and human factors. And today you get 3 for 1. So we're going to be focusing on 2 key themes. You'll be pleased to know you don't have to listen to me for 45 minutes. So the first plays to our strengths in understanding end user requirements and physical interaction. So that's more the human factors engineering side. So Hannah MacFarlane is going to talk about maintenance and maintainability. And for the second theme, Hannah Wright is going to talk about the importance of identifying and managing the risks at the organisational level, what we think of as more the human factors, socio-technical systems and social and organisational factors side of things. So I'm going to hand you over now to Hannah MacFarlane, who's going to talk us about maintenance and maintainability.
Thank you, Adrian.
Okay.
So as Adrian says, our first theme looks at maintenance and maintainability. We've discussed now how, by necessity, renewable installations are generally located in areas that are remote and hostile for human work. That presents challenges for both construction and maintenance of the installation. We're going to focus particularly on maintenance. Renewable installations tend to be largely passive during their normal operation. They rely on natural forces and are monitored and controlled by computer systems. From a safety perspective, as well as a cost perspective, this is a good thing because it means fewer people need to be on site. However, in the design of systems or components like this that receive very limited human interaction, there might be a tendency to give them limited attention. The basic type of quantitative risk assessment is essentially a calculation that considers likelihood and consequence. If there's part of a system that doesn't need to be accessed very often, little thought often goes into the design of access to that part of the system. If someone does need to get to it, they can simply find some steps or a ladder. The irony in this is that maintainers spend their days going from one system to another which has been given minimal consideration in design because individually each is infrequently accessed, and individually the consequence of failure or accident is considered to be low risk. As human factors practitioners, we push back against this. It shouldn't cost any more time or money to relocate human-machine interfaces to more accessible locations. Just a bit more thought and forward planning at the beginning of the design process. It's a frustration human factors consultants often face that designs are accepted or perhaps more accurately pushed through at design review when stakeholders are invited to comment on the basis that it's too late or it would be too expensive to change the design, when in reality the design is still only on paper or on CAD. So if that's really the case, why are we inviting stakeholders to comment? Okay, yes, sometimes we have to make compromises in design. Sometimes it's simply not possible to relocate these interfaces. It would just be inefficient. Wind turbines do have to be in windy places. And sometimes that's true. We have to live with a little bit of poor access as long as we can argue that the risk is a lot. But often with a bit of inventiveness, we can make these solutions better. These vertical axis wind turbines are a good example of how a different approach can be advantageous for installation, accessibility and maintainability. There is a minor loss in efficiency, but that's more than made up for by the reduced costs at installation and through life. Efficient and innovative solutions can also come on a small scale. The company Icewind have developed this highly efficient wind turbine which has little to no maintenance for 20 years, whereas a conventional blade turbine needs maintenance 2 to 3 times per year. So, risk assessments conclude that it's acceptable for an interface to be difficult to access on the basis that its frequency of use and consequence of accident are considered to be low. The paradoxical impact of this, however, is that every maintenance operation takes longer and is more hazardous than it needs to be. There's more system downtime when maintenance needs to be done, and more time and money is spent training maintainers or hiring specialist contractors. More time and money is spent setting up in order to provide access to hazardous locations, such as installing static platforms, scaffolding, or using MUPs. More personnel are required because hazardous work can't be completed by individuals working alone, or because the work needs to be checked and supervised. More time and money is spent on administration because greater risk assessment is required and safe systems of work need to be put in place. Risk is then exacerbated because more complex paperwork increases the risk of administrative error. So in maintenance of renewable installations, operations are overtly more risky because of the hazardous working space, whether confined, exposed, remote, or at height. But due to variation in system design, there's also more time at risk because each system is slightly different and maintainers are less likely to be familiar with the arrangements. So this increased time and cost and the frustration that come with that creates a negative feedback loop, which increases the risk of poor human performance in decision making, and that has multiple consequences. First is the probability for human error, which could lead to an accident and potentially physical injury. On a big plant, you'd expect local first aid or emergency medical facilities, but that's a luxury you just don't have when you're on top of a residential roof, 75 meters in the air on top of a wind turbine, or just in the middle of nowhere. Emergency access is then doubly impacted. It takes longer to get to the injured person, and then it takes longer to get them out as well. Second is the risk of latent error. Time pressure, complex and novel situations, and a difficult working environment are all negative performance shaping factors which increase the risk of a mistake being made, which could potentially go unrevealed for a long time. Then when the system does fail and a repair is required, we're back to the beginning. The increased use of algorithms, programmable logic, and AI to operate complex and distributed systems also contributes to the risk of a latent error being made. Computers and engineered intelligence systems are often much better at monitoring and detecting faults, so using more and more of that technology does make a lot of sense. However, the allocation of budget to software design, development, and testing is often insufficient relative to its complexity and risk. So introducing programming and automation doesn't necessarily eliminate human factors risk, it just shifts it to the left. The risk lies with programmers rather than operators. Computers may be more reliable and repeatable than humans at many tasks. However, they can still be programmed by a human to be reliably and repeatedly wrong, and that might not be found out until it's too late. Back to maintainability. Hopefully it's clear by now that early human factors intervention, or at least good design, is a good thing. Risk is reduced, and as a result, time and money is saved on every job. The potential cost savings over the course of the operational lifetime of a plant could therefore be huge. So why do we keep designing systems that are difficult to operate and maintain? Well, there often isn't an incentive for system designers to consider the future operating costs other than system energy usage or resource efficiency. Also, design and installation for big plants tends to be kept completely separate to the organisation that employs future operators and maintainers. Operators and maintainers tend to be busy operating and maintaining, and they often don't have time to come and look at or review new systems. In some cases, a system might be so new that there aren't even any operators or maintainers to engage in the design phase. The ideal model, of course, is involving these end users in the development of new systems and interfaces. In some technology development firms, particularly those in the medical and pharmaceutical industries, they'll pay end users or ex-end users to come and help them to design products that have a competitive advantage. So during the procurement phase of a project, budget needs to be allocated for operators and maintainers to be involved early in the system design from the beginning as key stakeholders. It's much easier and cheaper to take that advice early on than have to go back and change the design later. This brings us to our second theme, where we'll go to the other end of human factors intervention, where Hannah Wright will be looking at not the immediate health and safety concerns for the operator, but a broader assessment of why accidents happen.
Thank you, Hannah. So, why do accidents happen? First of all, we need to set the scene. We've already established that many of the conventional risks associated with power generation are not going away with renewables. We have big machines and concentrations of hazardous materials in hostile environments. Where there is risk, there's the potential for human error and therefore accidents, and the risks are more likely to be distributed over a larger geographical area with key concentrations of higher hazard plants. Although there are some big players in the development of large-scale renewable power generation, the balance of incentives is also attracting a large number of smaller companies and investors. We're seeing smaller organisations who have been sitting on novel technologies stifled by oil and gas for decades suddenly breaking into the emerging market as investment, and the changing climate makes their products economically viable. These smaller organisations are installing and operating lots of different technologies across multiple different sites, and they're more likely as the multinationals see these smaller companies nibbling at their profit margins, they'll swallow them up. It's already happening. So BP has bought ChargeMaster in competition with GridServe. Suez have partnered with EnergyX, which has lithium extraction technology. Scottish Power team up with Shell for floating wind farms. And Assystem and Atkins have joined forces to tap into the €20 billion French investment in renewables. So at this point, I'm starting to worry, because what are governments, big business and fragmented industry absolutely terrible at? Learning from past mistakes. And why? Because memory is flawed, it's expensive, and it's difficult. So let's review what we've learned over many decades of investigating accidents. Here are some of the most often quoted contributors to disasters, such as poor understanding or poor quality of information, poor communication, a toxic culture of cost-cutting, poor maintenance, incentives to violate safe practices, poor management of change or just poor management in general, a lack of investment in resources such as staffing, outsourcing to contractors, flawed risk assessment or a poor safety case which fails to identify significant hazards, and blame culture, inducing fear of speaking out or taking action and personal consequences for whistleblowers. And where have we seen this combination of toxic factors before? Well, I could rattle off a long list of disasters from Challenger to Nimrod, Chernobyl, Fukushima and Deepwater Horizon, and only one of these was caused by a natural world event. If you haven't seen the mini-series on Chernobyl or the Deepwater Horizon film starring Matt Damon, they are essential viewing that perfectly dramatise a lot of what I've just covered here. Okay, but these weren't renewable projects, so these risks don't apply, do they? So what about hydroelectric? The maintenance of old dams is a big issue for America thanks for years and decades of underinvestment. Elsewhere in the world, massively complex and ambitious projects are failing and resulting in ecological and socio-economic disaster. Take the Three Gorges Dam in China, for example, the world's largest hydroelectric plant. It's deformed and on the verge of collapse. Many provinces downstream of Yangtze have already flooded, and if it did collapse, it would submerge many towns and cities. And where there are slim profit margins, time pressure and productivity, utilisation and cost targets, there is risk. Is there any reason to think that these factors are going to be any different going forward? I'm not seeing it. There is no difference. So as the environmental imperative, legal, political and economic climates are creating a positive rush in the development of renewable power supply, it's a very competitive market and the margins are slim. These factors can incentivise a race to the bottom when it comes to minimising capital expenditure and operating costs. The old age battle ensues as the unenlightened see the cost of safety as a dirty impediment to profitability. The statistic Adrian mentioned earlier about how the UK has basically replaced its coal generation energy production with renewable energy, 40% in the last few decades, that wasn't achieved or driven by eco-sentiment. That was pure economics and market forces. Burning coal is just not economical in the UK anymore, especially compared with wind and solar power. The same conclusion is being drawn around the world, but it won't be true for everyone for many decades yet. So where significant hazards like nuclear material management force organisations and people to work together to mitigate risks, because the catastrophic consequence of a single incident are not tolerable. As we've already said, a feature of renewable energy production and delivery is that it's much more likely to be fragmented and distributed across many different sites. So attention isn't focused, there's an element of silo working and not connecting the dots. Renewable technologies are considered to be inherently safer, so we can be complacent. Surely solar panels just need a clean every now and again, and there's been no wind turbine related catastrophe yet. But solar farms have been experiencing fires and solar panel batteries are being recalled due to hazards. The Building Research Establishment was commissioned to look into the risks associated with solar panel systems, because we're increasingly fitting these to our rooftops, and they're becoming increasingly more powerful. The risks need to be more widely understood and minimised. Similarly, wind turbines can catch fire. The first death relating to wind energy happened in 2013 when a windmill in the Netherlands caught fire, and there were reportedly over 500 safety incidents related to onshore wind farms in the UK during 2020. If a single power station had 500 safety incidents in 1 year, that would certainly get the attention of the HSE. And to be fair, the risks from the adoption of renewable technologies are not going unnoticed. 10 years ago, the HSE published a paper on health and safety in the new energy economy, and they recognised many concerns in their foresight report on energy. So the HSE are preparing for energy transition, but I bet industry leaders don't have the HSE website in their favourite tabs. There are already calls from organisations like Safety On to improve data collection, communication and safety in this sector, because the collection of data on incidents and accidents is critical when the causes are so varied and distributed. It's the only way that we can understand the size of the base of our safety triangle and manage risks proportionately, because where there is risk, there is potential for human error. I'll now pass back over to Adrian.
Thank you. So, back to me again, and thanks to both Hannahs. I think there was some really thought-provoking content there that spans from the conventional safety aspects in terms of human factors integration with engineering and organisational and cultural factors, so we can apply our skills at both ends of the scale there. So just to conclude, summarise and wash up quite quickly, I think most people, when they think about renewables, they immediately think about wind farms and solar panels from a public perspective. But the growing demand for renewable energy is fueling projects at both extremes of engineering, which presents its own unique challenges. It is a rapidly evolving sector, operating on new frontiers at the cutting edge of science, and because much of the technology or the application of existing technology is new or it's never been done on such a scale before, lessons are being learned in real time. Now, there's no question that most renewable energy production is intrinsically better for the environment and safer for the public when compared to nuclear materials and fossil fuels. But in this presentation, hopefully we've illustrated that it isn't entirely risk-free. Far from it. In such a dynamic and changing marketplace, the old model of concentrated risk is changing, and risks are being geographically redistributed to potentially hostile locations. So we're moving away from the old model of having a smaller number of static mega factories. Renewable energy systems are becoming more distributed and geographically constrained to locations that present their own unique challenges for safety. So many of the conventional health and safety risks associated with power generation aren't going away. We've still got big machines, high power, concentrations of hazards and hazardous materials in challenging environments. And that mix of factors significantly increases the risk of faults or accidents occurring and increases the difficulty of managing, mitigating and recovering from any event. So history's taught us that what can happen when we don't manage hazards and predictable risks, whether they be physical or socio-technical. With renewables, we have a fragmented and competitive market. It's operating in novel and disruptive technologies, using concentrations of complex chemistry, high voltages distributed over large geographical areas, and they might be concentrated in hostile and even in residential areas. So we have the same problems, but we can view them through a different lens. And there are opportunities for intervention at every point, but obviously I'm here to focus on ergonomics and human factors. So for me, it has to start with a strong regulatory environment that has the capacity to legislate, monitor, enforce compliance. Luckily in the UK we have the HSE, which is great for us. Other countries around the world don't have the benefit of such regulation. We need to encourage businesses to conduct proper and proportionate risk assessment. We need to ensure that accidents and incidents are reported at all levels in businesses that may not have a culture of reporting incidents in this way. We need improved levels of certification required to install and maintain renewable energy systems. As I said, we've got new complex novel technologies that may be even fitted to our homes or in residential areas. We need to promote consistency in human-machine interface design to reduce the risk of human error. And we need to consider accessibility and maintainability as core requirements to improving safety. We need to engage with end-user representatives early in the design phase to optimize the designs, and we need to implement administrative systems to protect against poor design decision-making consequent of organizational pressures. Now, obviously, this takes time and money, but we have to accept the cost of preventing accidents or be prepared to pay the consequential price. Thank you.
Thank you very much, guys. That was very thought-provoking in terms of looking at renewables through a different lens in terms of the general public perception of that there's very little or no risk around the operations of such as renewables in terms of wind turbines, solar panels, and the others that you've mentioned. Do you think it's a case of well, maintenance crews, okay, they've been put into hostile environments, okay, but there'll only be ones and twos that'll be impacted. It's not going to be a mega number of people being impacted. Is that part of the problem here?
There's often a can-do attitude with maintainers in terms of they're quite used to living in harsh conditions and they just want to get on with it. But quite often, as we were saying, these things can be resolved during the design phase. We can easily make things better and make life easier for maintainers if we think about it very early on in the design, because the maintainers are bouncing from one rubbish job to the next, day after day. Yeah.
No, that's quite thought-provoking. Is the slide on the redesign of a wind turbine? If you get the design right, then you can eliminate quite a lot of the hazardous risks that a human would face in terms of carrying on with the design, carrying out the maintenance. Mm-hmm. So do you think that's beginning to creep into the design industry, or is that in terms of how engineers approach design? Clearly, we would all say that from a human-centric design point of view, that the human factors should start at the beginning of the design, not brought in at the end to rubber stamp a particular design. Are you seeing changes in the industry in terms of putting the human being at the center of design?
Some industries, yes. Some industries, no. Obviously, the nuclear industry is really good at incorporating human factors. It's in the regulatory tags and things like that. So we get in early. But the renewables industry, it's outside of that regulatory framework in many respects. They're perhaps not used to talking to or dealing with human factors experts. So that's something we'd like to change. It's partly why we're here today.
Maybe there's a piece for the HSE in terms of education, and perhaps the environmental agency in terms of further education and knowledge, which could be shared from the experiences from the nuclear industry, perhaps, in terms of how to go forward. Well, I must say thank you very much, guys, with that presentation.